Hello everyone, and welcome to another member sponsor video hosted by Mr. Logan Frank. Alright Logan, in this video we're going to be continuing on with our little mini series, putting together a Pong game with Python. What is it that we're going to be doing in this video?
Well, I want to get some of the base classes put into place. What we're going to focus on in this video is creating a Vector2 class and an Actor class.
Okay.
The Vector2 will allow us to store a variable with an X and Y component, and the reason I wanted it to be a class was so that we could give it, you could say, methods that make it mimic a numeric type.
Okay.
That means that we can take this vector by itself and multiply it against another vector, add it against another vector, add it against a scalar, multiply it against a scalar. A lot of convenient numeric operations will be available with it.
Nice.
And just a side note, I know that we don't have to go into vectors to make a simple Pong game. We could use integers, we could use floats,
Sure.
that would be just fine. But I really like working with vectors when controlling on-game objects, or in-game objects. So this is the route I've chosen.
Okay.
And once we get these classes in place, the Vector2 and the Actor class, I will go in and make some a temporary object that we can see on screen and implement enough of the draw and update methods just to verify that our code is working.
Okay, sounds good.
So let's get started. This is all going to begin with the Vector2 class. And what we're going to do is we're actually going to jump in just below our game settings. We'll leave that at the very top just for convenience sake, so that if we want to change the game later, the first thing presented in this script are the game settings themselves. So down here, let's jot down a comment called classes. We'll designate this area of the script to be for classes. And we'll begin the Vector2 class. So we'll say class, Vector2, and then we'll jump in first with an init method. I want this Vector2 to work such that whenever a Vector2 is created, one must specify or it will have an X and Y value. I'm going to give defaults for both of those so that if you want, you can create what looks like an empty vector that will auto-initialize to a value of 0, 0.
Okay.
So let's get that in place. Let's define an init function. And to that init function, we're going to make sure that self is passed in, because we're going to be calling this as an instance of Vector2. And I'm also going to specify an X value and a Y value. Though, again, I will default both of these to 0 so that they may be omitted when creating a new Vector2. So that way it will auto-default to a value of 0, 0. Now, the code here is to simply make sure that two attributes get added to the Vector2 class, and those are the X and Y components. So we'll make sure that self.x is set to the value given in x, and self.y is set to the value given in y. So as simple as that. Now, the next thing I want to do is, like I had said briefly before, I want this vector class set up so that it acts as a numeric type, so that I can directly add and multiply vectors. Now, I'm not going to give a complete implementation for a vector class. That means I'm not going to include things like subtraction, division, and many other mathematical operations. I'm just going to get the basics needed for this Pong game. Now, of course, seeing these, you're completely free to go ahead and implement whichever ones you like to make a more full-featured Vector2 class. But this gets us up and running in a smaller amount of code just for this demonstration. Now, the first operation I would like this vector to be able to do is to add. I'd like to be able to add two vectors together, and I would also like to be able to add a Vector2 with just a number. So that way, if I want the overall vector, both components to be increased by that number, I'll just specify it. So let's define the add function. And to that, we're going to take in self, so we can see ourselves as an instance, and we're going to take in other, so whatever else is being given in the add operation. So once add is applied to a Vector2, self is this instance, other is whatever we're being added against. Now, since there are different considerations in whether other is a vector or a scalar, meaning that if it's a vector, we want x and y to be added together individually. If it is a scalar, we would like x and y to both be increased by whatever value is in other. But that means we need two different types of functionality to happen if we have a scalar or a vector. So what I'm going to do is to do a simple check that does a check to see if other is a Vector2 instance. If it is, the code is treated as a Vector2. Otherwise, it is treated as a scalar. Now, again, I'm sure more checking code could be done to make sure that the Vector2 doesn't explode when you add it to a string or other considerations like this. But this is just the code required so that I can both add it to scalars and vectors later in code in the game. So let's begin an if check to determine whether or not this is a Vector2. I'm going to use the isInstance function in order to find this. So if isInstance for other and vector2, so if this resolves to true, that means other is an instance of vector2. If it resolves false, then it is something else, and I'll simply assume that it is a scalar value. So if this is in fact an instance, what we want to do is return a new vector2 representing what the addition would have been. So we will return a vector2 where we feed in the current vectors x plus the other vectors x. And we also want to specify y values. So just for readability's sake, I'm going to jump down another line to specify the y component of the new vector, which is going to be equal to this current vector self.y plus the other vectors y. And that finishes off our new vector. Now, if the other variable or the other argument was not a vector, then we'll treat it like a scalar. So we'll drop in an else, and in that case, we'll return once again a vector2, because even if we add against a scalar, it's still a vector2. And before I jump into that, let me make sure I add in my colon so we jump into the else statement. So we're returning a vector2. The vector2's x component will be self, so this vector2's x plus other. Because if other was a scalar, something like 5 or 2.5, we'll add that to both x and y in this new vector. For y, we'll of course look at self.y and add that to other as well, and that wraps up the else statement. So that takes care of addition. Now we would also like our vector2 to be able to work with multiplication. So I'm going to copy the entire add function, paste it again, but change the function name itself to mul. So this will allow us to respond to multiplication. Again, keeping the same system here where we have self and other as arguments passed in. We again do a check on other against vector2 to see if it is an instance of vector2. If that's the case, we treat it like a vector in the, well, I was going to say in the addition. Here we are looking to do multiplication. So the one change we will do is make sure that the arithmetic here is multiplication.
Right.
And that will take care of everything, and everything else is left the same. The same idea can be multiplied against a vector or multiplied against a scalar.
Okay.
And one last thing I want to add to the vector class is just something for convenience sake, and that's the ability to set the vector2 back to 0. There is a place later in code where it becomes convenient to make sure we reset a vector, and I want to make sure I do that without having to create any additional instances. So what I'm going to do is I'll define one more method, this method called set0. Set0 only taking in whatever the current instance is, and its job is to take the current instance of vector2 and make sure that its x and y components are equal to 0. So self.x equals 0, self.y equals 0, and that's it. Again, more of just a convenience factor, so I can very easily zero out a vector2. And that really wraps up the vector2 class. Now we can turn our attention to the actor class. So to define that class, we'll say we'll have class actor, and the actor class is going to begin with an init method, because I'd like to have several things set up whenever we create actors. So again, we'll define an init function. We'll take in the current instance, and we'll also require a texture parameter. And that texture is going to be a surface, same thing that we had loaded in the example little game window where we had that one graphic loaded. I'm going to require that actors have a surface given to them on creation, because actors are going to use surfaces in order to draw. So I want to make sure that we have to have a surface from the beginning for the actor to even exist. Then, to this actor, I want to make sure that we set up some attributes. I want the actor to have attributes like position and velocity. Again, if you remember to that quick app, which actually probably covered more things than I was intending it to, we saw that we had, in order to move an object around the screen easily, we needed to store two pieces of information. We needed to store a position, and we needed to store a velocity. I'm going to do the same thing in actor, but this time all of these attributes will be instanced to the actor itself, so we can have as many sets of these as we want, and they're all contained within actors. Now again, the first one is going to be position. So I'll have position, and we'll make sure that that is initialized to a new vector 2. And again, that's where it's convenient that x and y default to 0, because we're not going to specify the position yet. We'll make sure that the any newly created actor exists at position 0, 0. But moving on, we now have the velocity. And the velocity attribute is going to be set to a vector 2 as well. And then one last thing we want to make sure we have set up is we'll make sure that self.texture is equal to texture. So make sure we remember that surface reference over to that texture we feed in. And let's see, several other methods. One method that is very useful to have inside of the actor would be the ability to get a rectangle representing that actor, the space that actor occupies on screen. Now, I know we can get the rectangle out of a texture, but the problem is we're not going to be moving that rectangle around. We're going to be moving the actor's own position vector around. So in order to get a rectangle that represents this actor, we actually need to be able to make a new rectangle that is based on both the position and the texture's dimensions. So we actually read from a little bit of both and make a new rectangle. So I'm going to make a method here called getBounds. And we're only going to look at the current instance. And inside of this, we're going to return a new rectangle. So return, and the rectangle type resides in Pygame in our case. So we'll look at pygame.rect, and to make a new rectangle, we'll specify an x, a y, and a width and a height. So the x is going to be given by our current position x. So that is self.position.x. And each of these components I'm going to specify on their own line, again, just for readability's sake. So we'll jump down the line and give self.position.y for the rectangle's y value. We'll give self.texture. Now to get the texture's width, we have to first get its rectangle. So we'll make sure we call getRect, and then from getRect we can look at the width returned. And then for the height, same thing, we'll look at the texture. We'll run getRect, and we'll look at the height returned. And that wraps up the new rectangle, and that also wraps up the method getBounds. Moving on, the next method I want to have is a move method, a method that we can call, specify a vector 2 for the amount that should be moved, and have this actor's position updated to reflect that movement. So we'll define this as the function move. We'll take in the current instance and how much to move as an amount. So with this defined now, we'll set it up so that we can say self.position will be incremented by the amount specified. Simple as that. Now, moving on from here, two more methods I want to have set up, and those are methods that will allow an actor to center itself on the screen. Since we have, in fact, specified globals in order to hold screen width and screen height, we can see those from the classes. Interesting point to note is that they don't necessarily have to be physically before the classes. They simply have to be in existence before the class is created, or at least before that method is used. So we can see the variables simply because they are global compared to the actor, not necessarily because they happen before the actor. But nonetheless, we're going to start using those so that we can make an actor able to center itself on the screen. So I'm going to define a new function. This function is going to be called centerY. And we're only going to look at the current instance. And what centerY is going to do is it's going to look at screen height, divide that by 2. It's going to look at this actor's own height and divide that by 2 and subtract that from the overall screen height, thereby centering on both of them. So basically we get the screen center, then we get the actor center, and then offset by that actor center so that everything is visually aligned in the center of the screen. So to do this, we're going to look at the current instance of actor, tell it that its position in Y is going to be equal to the current screen height divided by 2, and then we're going to offset again by however y, or basically wherever the center point of the actor was. So that is going to be self. Now to get the height, we're going to look into the texture. So self.texture.get rect dot height, and then we want to divide that height by 2, so we get everything nicely centered up. Now moving on from this, I'm also going to make a method that will center on both x and y. So we'll define center xy, same as center y, we're only looking at the current instance, and in this case self.position will simply be set to a new vector 2. And to that vector 2, we'll simply specify its x and y components right off the bat. Now to save time here, we have already come up with the formula necessary for centering a rectangle onto the screen itself. So I'm going to copy that line, paste it here, but I'm going to change height. Actually, I'm going to change height in just a moment because we do need this calculation when we specify y for the vector 2. Now to specify y, I'm going to give the comma so we move on to the y component, but I'm going to drop down to a new line so that all of this fits on the screen. I'll paste the line in again. The reason I refrained from changing it is because we're going to leave the line unchanged for y, but we're going to change it to look at width when centering in x. So that is screen width divided by 2 minus the texture's height. Only height here is going to be changed to the texture's width. So screen width divided by 2 minus texture height, or excuse me, texture width divided by 2.
Mm-hmm.
Then we can finish off the vector 2, and that takes care of center xy. Now, you'll note that I'm not going to put in a center x function here. That's simply because I did not need one in the creation of this game. And I'm also trying to keep the code relatively short and succinct just for the purposes of recording here. So, moving on now, we've got a vector class, we've got an actor class, and so what I'm going to do is I'm going to call it a temporary object. I'll make the ball for the Pong game, but it is going to be set to an actor just for temporary purposes. In the final version, we'll have a ball class to handle some ball-specific functionality. Now, one thing I'm going to do before I create that object is I'm going to load in some textures. So at this point, what I'm going to do is jump in right below our initialization and actually make a new section for our game. I'm going to call this section textures. And that way, before assigning the textures, we'll hold them in variables. So that way, some things that use the same texture, like the 2 player paddles, can look at the same reference, and I don't have to load the texture twice. So the first variable I'm going to call ball texture. And to that, we'll store pygame.image.load, and load will be loading in the ball.png graphic. That, of course, residing in this directory, the Python project's Pong subfolder. Now I'm going to copy and paste that line so that I can make another variable, this time called player texture. It could also be called paddle texture, because what we're going to store within it is the paddle graphic. Alright, now that we have some textures loaded in, we can create our first actor. So what I'm going to do here is jot down another section, another comment that I'm going to call game objects. And inside of game objects, let's create an actor now. I'm going to make a ball variable, but to that ball variable, I'm going to store a new instance of actor. Now, of course, actor is going to require a texture in order to be created, so I'm going to feed in ball texture. And that is, of course, why we have our textures loaded in ahead of time. Now, I'm also going to set up this ball's velocity. So I'll say ball.velocity will be equal to a vector 2 of maybe 1 in x and 2 in y. And I'm just specifying so that we can see some motion on the screen to verify that our actor class is indeed working. Alright, now that we have an instance of ball created, we need to update, or we need to add some code to our draw method, because at the moment we're calling draw, but draw does nothing, it returns none. So we need to put some actual drawing code here in draw. So I'm going to erase the return none, and we'll put some actual drawing code in place. Once again, we're going to use the screen surface, and we're going to begin by filling the screen. Now this time, instead of specifying a sequence directly, we already have a variable up in the game's settings section called color black, which is already set up to the values 0, 0, 0. So we can use that down here, now making it more convenient to keep track of what we're doing. Down here in the draw method, we'll fill to the color black. Now, once we have the screen cleared out, we need to blit the ball's texture to the screen. So I'll look at the screen, tell it to blit the ball.texture, and we're going to give that a, instead of specifying a position, one of the other options here is to specify a rectangle for the positioning. And we have taken the time to give a getBounds method inside of any actor. So an actor can give its overall area on screen, including position. So we'll give in ball.texture for the texture and ball.getBounds for where this should be put on the screen. So ball.getBounds will be fed into blit, finish off the call to blit, and that will take care of getting our ball texture painted onto the screen. One last thing to do is remember to call pygame.display.flip. So now we flip the back buffer onto the front, and we can see what we've just drawn. And now I believe we should be able to run. I'm going to run primarily just to check for errors, but what we should see is the ball graphic being drawn, that small X graphic being drawn. We'll note that it won't actually move yet. But let me go ahead and run. There doesn't appear to have been any errors since everything is drawing, and we have that little green X drawn up in the corner. And also note, it is not moving. This is because we have not implemented update yet. So, that test worked incredibly well. And now back in the code, I'm going to address update. Inside of update, I'm going to do a few things. First thing that I want to do is I'm going to make what I'm going to call a time factor variable. The idea here is that anything that gets moved will be moved by the elapsed time. But the value given, if you use elapsed time directly, is a very fast value. Using something like 1 and 2 to drive the ball will result in the thing moving very quickly. And I would rather have it move at a slower rate. Now, to demonstrate that, before I actually put the time factor in, let me move the ball by simply using the velocity and the elapsed time. So inside of update, if we tell the ball to move, and then we give in the ball's velocity, as a matter of fact, that alone should work. Because again, we're specifying a vector here, so we're going to move by a vector, and that vector should currently hold the value 1 by 2. So if we run, we didn't see the X running, but it was running very quickly. And it's also running in a manner that will vary depending on how fast the target computer is actually running at. So a faster computer will actually cause that to move more quickly.
So go ahead and run it one more time.
So running one more time, so very quickly we see the X run from the top left of the corner of the screen and then exit off the bottom of the screen. Now, in order to make this adaptive so that it will move the same speed on any computer, what we can do is factor in our elapsed time. So back up here in update, we instead multiply ball.velocity by elapsed time. Then we should get a velocity that is the same no matter how fast the target computer is running. Now, of course, I'm sure there is some margin of error here because the millisecond value we may end up with rounding errors based on that. So it might not be an exact pixel per pixel speed, but it should adapt nicely so that you don't see a computer being 5 times faster causing this thing to move 5 times more quickly. And again, just a quick explanation here is that if elapsed time on a slower computer, elapsed time will be larger because if there is a slower frame rate, more time goes by per update. That means we have larger values here. So on a slower computer, ball velocity is multiplied by a larger value, and vice versa on a faster computer. Now note this. If I use elapsed time directly, we're going to get some very fast movements because we're going to have values like maybe 16 if the game were happen to be running at 60 frames a second, or smaller if the game's running faster. But again, if we're looking at 16 times whatever value we're getting here, that's going to be a very fast value. So if I run, watch very carefully, and you might see the X just for a split second before it exits the screen. So what I've done is I've come up with a factor that I'm going to use here just to make these values a little bit more usable for on-screen moving. And so I'm going to call this variable time factor. And time factor is going to be equal to the elapsed time. And I think elapsed time is a capital T. And we'll multiply that by the value 0.05. And now the explanation on this value is it's just whatever worked at the time. Again, we had mentioned that the code is presented in a prototype fashion. So I haven't even gone through the effort of making that into a setting, simply because it's not based on anything other than preference. I just went through a few values and this happened to work. And if you wanted to work out the math, you could do things like amount of time it would take to cross the screen, amount of pixels crossed per second. There are a lot of solid values you could base this in, but I've gone with 0.05 because it lets me use values in a range of about 1 to 10 as good on-screen speed values. Now we do need to remember to use our time factor variable instead of elapsed time here, and now if we run, we get a much slower movement, much more controllable, and much more useful.
Nice.
And with that, I think that's really all I wanted to accomplish in this video. Again, just a quick recap is that we have created a Vector2 class, we have created an actor class, and then we turned around and made a simple temporary version of the ball object using our new actor class to make sure that both actor and vector were working to give ourselves position, velocity, and then we went and gave a simple implementation for update and draw so that we could work with our actor and make sure that it's drawn to the screen to give a good visual result.
Excellent job, Logan. All right, guys. Well, with that, that is going to wrap up this video. Thanks a lot.